So this is session number 18. We're getting there almost at the end of the semester. So Monday, October 31st, and this is Calculus 3. And today we'll discuss two topics, double integrals in polar coordinates and triple integrals. So double integrals in polar coordinates is a really interesting topic where we tie some ideas together. Okay, the whole idea of viewing curves in a slightly different coordinate system. And then we'll also answer this question, why? Like, why do we care, right? What's the big deal? And the quick answer to that is that some integrals, if you were to compute them in rectangular coordinates, are just too complicated. Now, of course, they can be done numerically and machines can do it for us, but we can make our lives much, much easier if we convert our curves and regions of integration into polar coordinates. And eventually, you'll be able to recognize when is this time to use different coordinates, right? So unless, of course, it says right away, oh, compute this integral using polar coordinates. Well, if you don't know, how would we recognize it? And it is all about what the region of integration looks like, okay? So first, let's go ahead and get used to this notation and the way we describe these integrals, not integrals, regions of integration using polar coordinates. Okay, so here I have two rectangles. Okay, they're not rectangles in the sense that we think of them. They're polar rectangles, so they're not going to be just boxes. Okay, but what a rectangle looks like. So R1 here says it's all points are thetas, so that r is between 2 and 3, and we have theta between pi over 4 and 5 pi over 4. Okay, so I'm going to go ahead and sketch it. Now, I am working with a polar plane, right? So this is no longer xy, this is r and theta. And I usually start with the angle. So my angle right here is between pi over 4 and 5 pi over 4. So I'm going to go ahead and mark these angles. So this one is pi over 4, 5 pi over 4. That would be third quadrant, right? So this one right here. So that's where my angle goes. I'm going to kind of indicate the direction, right? So I'm going to go this way, right? What about r? Radius, right? So r goes between 2 and 3. Okay, so if I were to kind of mark this as my distance, let's say this is 2 right here, and this is 3, okay, then you can make the circle. Let me go ahead and make it everywhere. So here's my circle of radius 2, and then this is a circle of radius 3. Okay, but we are bounded with the angles, right? So the angles are between pi over 4 and 5 pi over 4. So what I get is this piece right here. So we would be integrating something over this region. Not exactly a rectangle that we're used to think of, right? This is definitely not a box. All right. So R1 is this, what would you call that? Half a washer, right? Okay. So that's your R1. All right, let's go ahead and make another sketch. So for R2, what does that look like? Okay, again, I'm going to start with the angle. Now this one starts with the negative, no problem. That's fine. We know what that looks like. So negative pi over 4. So starts right here. And then 2 pi over 3. So it's an angle over here in this quadrant. So this is not symmetric, right? Okay. And then what about r? So between 1 and 4. So let's say this is 1, and then 4 would be here. So you make your circle look something like this. Okay. And here is my second region of integration. This one is not necessarily symmetric. That's fine. It doesn't have to. Okay, so here's theta 1. You can think about it as the lower limit, negative pi over 4. And then theta 2, that's 2 pi over 3. And let me go ahead and label my r's. So lower limit for r would be 1, and upper limit for r would be 4. Okay? All right. So just sketching these regions of integration, part of your homework will be something like that. So here's the picture. Set up the limits for r, set up the limits for theta, just by looking at the picture. Okay, don't integrate anything, just get a setup ready. All right. So take a look at this, guys. Let me know if you have any questions, if you want to discuss anything, and then we'll get to the actual integration. How's this problem, or this example rather? All good? See a couple of thumbs up. All right. Okay, then let's take a look at the actual integration. So here's a formula. That's a general formula for the integral of a function over a region that we can describe in polar coordinates. Okay, so we're not going to derive the whole thing. So that's not what this class is about. It's more of an application class. But what does it say? So it says the following. Once you determine your limits, right? So here I have B and A. That's my limits for R, and alpha and beta. Those are my limits for theta. And you would do that by sketching the region of integration and identifying what are the limits, right? So what does that look like? Once that's done, what else do we need to be concerned about? We need to rewrite our function in terms of r and theta. So this is conversion, right? This is converting the curves um, in terms of x and y now into a function of r and theta. So that's something we've covered at the very beginning of the class, and now it's coming handy here. Okay, so you would take your function of x, y, and convert it into a function of r and theta. Okay, and also you notice that there is this r here. That's not a typo. That is part of the formula. Okay, so you would be integrating. The integrand would be f of r theta times r. Okay, now it's there because the way we compute the area of a sector. Okay, so we're not going to derive the whole thing. If you're interested in seeing why that part is there, you can take a look at the book. It goes through the explanation. Okay, but you don't need to know, and you just need to remember that that is part of the formula, and that's maybe something, as part of the formula as you're preparing for your next exam, make a note of it. Okay, that R needs to be there. Okay. So let's go ahead and apply this formula to the first example. It says find the volume of the solid below this paraboloid and above the region R, where R is between 1 and 2 and theta is between pi over 2 and negative pi over 2. So I'm going to go ahead and make a sketch of R. You don't always have to do that, but I think it's a good idea to make those connections, right? What does that look graphically? And we should be able to convert this representation into a picture. Okay, so negative pi over 2 to pi over 2. So we go from here. So this would be negative pi over 2, right? And then this would be pi over 2. And what do we have? R is between 1 and 2. So it would look something like this. Okay, that's our region of integration. Okay. So that's our polar rectangle. All right. Now what do we do? Okay, we have our limits, right? So we have the limits over here. We're going to plug it in into the integral eventually, but first things first, let's go ahead and rewrite our function in terms of r and theta. Okay, so what does that look like? Okay, so our z, or the function of x and y, let me go ahead and write it this way. It's 4 minus x squared plus y squared. And you might recall that this is just r squared. So those equations that relate polar coordinates, right, to rectangular, we just need to keep them in mind. So our function is just 4 minus r squared. Okay, so now we can set up our integral. The volume is then this double integral of what? What's my function? My function is 4 minus r squared. And now r, that's from this formula right here, right? Okay. And then dr d theta. What is my r? What are my r limits? From 1 to 2, that's for r. And theta goes from negative pi over 2 to pi over 2. Okay, that's the setup. And now integrate. I'm going to do the inner first. So we're going from 1 to 2. If I multiply this through, we get 4r minus r cubed dr. It's a simple polynomial, right? We can do this. So this would give us what? Let's see, 2r squared minus 1/4 r to the 4th. We go from 1 to 2. Okay, so if we evaluate this, this is 2 times 2 squared minus 1/4 2 to the 8th power, and then minus 2 times 1 and plus 1/4. Okay, if we do this carefully, we should get 9 over 4. Just plug this into your calculator. Okay, and then the outer integral is then simple because it doesn't even depend on theta, right? Okay, so that's nice. That's just 9 over 4 d theta. So we get, this is theta, evaluated from negative pi over 2 to pi over 2. So this is pi over 2 minus minus gives us a plus. So we get pi, and the final answer is 9 pi over 4. And this is volume, so this is cubic units. Okay. All right. So that here's your first problem where we used polar coordinates. Okay, now let's just think about it for a minute. What if we didn't, right? So what if we did not use polar coordinates? How would we go about it? Well, let's see. So if we were to use rectangular coordinates, we would have to say, okay, which direction do I need to go first? And then you can see that, okay, so here, it's difficult. It would be difficult to pick one, right? Because if you go in this direction first, in the y direction, then once you get over here, you have two different limits, right? Okay. If you go in the x direction first, you have the same problem once you hit this this vertical edge right here. So you would have to split this up. You would have to split it up into several pieces, but also just integrating the function where you have these limits. So this limit right here, this limit, would be something like what? If this is the square, I'm sorry, this is a circle of radius 2, so it would be something like this. X is equal to square root of what? If it's radius 2, so it would be 4 minus y squared, right? So you have to find it, but also imagine using this as the limit of integration. It just gets really, really messy. Okay, and sometimes we can't even do it. We actually can't use our conventional methods to compute these integrals. The best we could do probably approximate if we were to use it with rectangular coordinates. But look at polar coordinates. It is so simple. There's nothing difficult about it. All we had to do, just look at it slightly differently and say, okay, let me go a different system. All right. So that's your example where we produced a sketch of the region of integration, converted everything in terms of r and theta, and then actually evaluated. What do you guys think? Does this make sense? Okay, so you will have a couple of problems where you need to compute um, the volume, right? So on your homework, that's kind of like a heads up. And it's kind of strange the way the homework system is set up. Half of them are really, really simple like this. And then the other half is on the other side of extreme. They're not too complicated. They just pick up these like really large numbers and the answers turn out to be big. Okay, so as you're working through your solutions, just keep that in mind. You're not doing anything wrong. If you're just writing things out carefully, you'll see that the numbers they just turn out large. Okay, and some of those numbers are randomly generated. That's one of the things that I kind of dislike about this program. Okay, now also keep in mind on the exams, I pick problems of this type where numbers turn out a little bit nicer and not so big and really kind of ugly. Okay, but as you work through your problems this week, keep in mind that you're not doing anything wrong. That's just what the numbers that you were given. That's how they got generated. Okay. All right, let's take a look at the next example. Let's see what we got here. Okay, same setup. Find the volume of the solid below this hyperboloid, okay, and above this region right here. Okay, so another R is given to us. That looks like an entire washer, right? So let's take a look at what that R looks like. Okay, I'm looking at my angle from 0 to 2 pi, so I get a whole revolution all the way around. But what about r? Okay, so r is bounded between 2 and root 3. So that's my region of integration. Okay, as soon as you sketch your region of integration and it looks something like this is a great indicator saying, yeah, we're gonna convert everything in terms of r and theta. Okay, here's your r, and also look at the function 5 minus square root of 1 plus x squared plus y squared. If we were to integrate this with respect to x and y, it doesn't even matter what the limits of integration are. This would be hard. Okay. Um, I don't even know how I would go about it because the u substitution would not work here. So this would be challenging to just do it by hand. Okay, so let's take our function. Our function in terms of x and y is 5 minus square root of 1 plus x squared plus y squared. Convert it into what? 5 minus square root of 1 plus r squared. Okay? All right. So now we can set up the volume. It is the double integral 5 minus this radical times r dr d theta. Okay, what are my limits? So r goes from root 3 to 2. Oh, sorry, the dogs are unhappy about something. And then radius, oh my god. Okay, sorry about that. People are walking outside my house, and that, if you have a dog, that triggers them. All right, so radius is set up. What about theta? That one is going from 0 to 2 pi. Okay, now let's take a look at this. Our integrand is in terms of r again, right? Okay, so you can say, oh, if I just compute the inner integral, you can see that then you just evaluate that from 0 to 2 pi, so you just multiply by 2 pi, right? Because 0 doesn't do much. So, and that's the beauty of most of these integrals. Most of the time, you'll get something really nice like this if we set this up carefully. Okay. All right. So let's go ahead and integrate the inner one. So we get the integral from root 3 to 2. And I'm going to multiply this r through. So this is 5r minus r times this radical dr. Okay. All right. How would we go about this? What would be the method to compute this integrals? What do you guys think? So 5r is easy, right? Not much to do here. But what about r times the square root of 1 plus r squared? What do we think? Yes, you can do u substitution here. Okay. So I'm going to let you figure that out. That's a method you should be very familiar with, right? So 5 over 2 r squared, that's the antiderivative for the first one. Okay. Here you will get negative 1/3 1 plus r squared to the power 3 over 2. Okay. I'll make a note here that you can use u sub here. And if that's something you need to review, go ahead. Or if you need help reviewing it, let me know. So we need to evaluate this between root 3 and, let's see. Oh, it's 2 root 2. Sorry. Okay, this should be 2 root 2. I'm not reading my limits correctly. Okay, 2 root 2. So that goes in here. And if we do this carefully, you actually end up with a nice number, or nicer, 37 over 6. Okay, so then the rest of it is what? So the outer integral would be from 0 to 2 pi. That doesn't depend on theta. So that would be 37 over 6 theta from 0 to pi. Oop, let me go ahead. Oh, yeah, this is right. So then this would be 37 over 6, 2 pi minus 0. Let's see, 2 and 6, we can reduce those. So this is 37 pi over 3. Okay, and that's your final answer. All right. Okay, so what do you guys think? What's the general feel of about this topic as of right now? You might feel differently, a week from now, but what about now? Does this make sense? Yeah. Okay. All right. Then let's keep going. The next problem, a little bit different. Here, we're not given the region of integration. We just asked to compute the volume of the solid bounded by the two paraboloids. Okay. So in this case, what you could do, you could just to visualize, just to see what that actually looks like, um, use Wolfram Alpha to see what those paraboloids look like. Okay. So I'm going to go ahead and sketch this because I know what they look like. So let's see what we're trying to figure it out here. So here's our three space. Okay. And I have paraboloid z is equal to 2x squared plus y squared. Okay. So what this one looks like, that is a paraboloid that opens up. I hope you can see that, right? So it starts at 0, 0 at the origin, and it opens up like this, and it has like an elliptical base. So it looks something like that. It's not circular. Oh, let me go ahead and put it down a little bit so the picture looks better. Okay, something like this. We just need to get a general idea what that looks like. Okay, and then the other one, let me mark this one. So this one is z is equal to 2x squared plus y squared. Okay, the other one is 27 minus x squared minus 2y squared. Okay, so that one is opening downward. Sorry, I had to mute myself so you guys don't freak out. All right, so let's take a look at this one. 27 minus x squared minus 2y squared. That one opens down this way. Okay. Again, I hope you can see the connection here, right? Why is one going up, one is one going down? Because the way our x and y are in the equation, right? Okay, so that one starts at 27. The first one starts at 0, 0 for z. Okay, let me go ahead and mark all of them here. So this is z is equal to 27 minus x squared minus 2y squared. And what we want to find is the volume that's bounded by the two things. Okay, so what something in common, right? And it's a little hard to visualize, but that would be how much space is taken over here, right? Okay. All right. I apologize for my dog's behavior. They're just not having a good morning. Okay, what do you guys think? Does this make sense? Just the picture? Yay, nay? Yes? Okay. I know it's might be a little bit challenging to like really make this connection between graphs, right? Okay, if you're not sure, just punch it in Wolfram Alpha. See what that looks like. But I hope you see algebraically why I was able to say, oh, that's what that looks like, and here's what this curve looks like. Okay, so now we want to find the volume that's between those two, but we're not given R. We don't have R. Okay, well, the R would be this intersection of them two. You can think about it as the intersection kind of projected onto the xy plane. Okay, they cross over at this circle. Okay, so how do we find that? Well, we can set these z's equal to each other. If we do that, we will find their cross section, right? The equation of their cross section. Okay, so what do we get here? This is 3x squared plus 3y squared is equal to 27, and we can reduce by 3 And we know exactly what that is. Okay, so this is R, all points. Let's convert it into R and theta, no more X and Y. Okay, what do we have here? Radius is between 0 and 3, right? This is 3 squared. And what about theta? That goes from 0 to 2 pi because we have an entire circle. Okay? All right. So now what? Okay, we have the region of integration, but what about the function? Well, the function would be the top minus the bottom, right? Okay, so it's very similar to what we've done with area bounded by two curves, right? So remember, area bounded by two curves. Oh, it's the top function minus the bottom over the region of integration. It's the same idea here. So the top would be what? 27 minus x squared minus 2y squared minus this other paraboloid. I'm going to put it in parentheses. Okay, so that's 27 minus what? We get 3x squared and minus 3y squared. And we can convert that to 27 minus 3 r squared. Okay, so our function that we're going to be integrating is this difference, and we can easily convert that into function of r and of just r and theta. Actually, just r, not of and theta, right? Okay, so now we can compute that volume. You'll see the integration part is always simple. Okay, it's the setup. So 27 minus 3r squared, and then we don't forget the r here, dr d theta. Okay, what are the limits? We go from 0 to 3 for r, from 0 to 2 pi for theta. You can see that at the end we'll just multiply everything by 2 pi, and that's it. So I'm going to go ahead and compute this in one line. So this is going to be 2 pi times what? Okay, it's 27r. The antiderivative is 27r cubed over 3. And then here we have negative 3r cubed. So that's negative 3r to the 4th over 4. We go from 0 to 3. Okay, at 0, everything vanishes. So we just need to evaluate this at 3. So 27 times what? 3 cubed, that's also 27. And then minus 3 times 81 over 4. Punch that in into your calculator. Okay, we're going to get 2 pi times 243 over 4, and we can reduce by 2. 243 pi over 2. Okay, all right. Okay, let's take a look at this example. Review all the steps. Let me know if there's anything you'd like to discuss. Any feedback, any questions? All good? Okay, I see thumbs up from Carla. How about the rest of you guys? No problem? All right. Then let's keep going. So now these last two problems will be dealing with the area of the region. How do we compute the area of the region, but using a double integral? Okay. So the first problem says sketch the region bounded by the cardioid. Okay, and yes, you would use graphing utilities here. Use Desmos. We don't need to do this by hand. Okay, to find the area, and then use double integral. Use double integral to compute the area bounded by this curve. Okay, so how do I go about it? Well, first let's go ahead and sketch it. And again, I'm just going to use Desmos. And if I plug in 2 times 1 minus sine theta, I'm going to get something that looks like this. Okay, where we have a cusp right here at this point. And that's problematic. That means we kind of need to split things up um, as far as the integration goes. We cannot just integrate from 0 to pi over 2 because we have a problematic spot um, halfway through. Okay, so but what is the general idea then? You said, okay, well, double integral, right? To compute area, what? Haven't we been computing volumes up until now? And the answer is yes, but if you set up your integral this way, let me go ahead and set this up. Okay, r dr d theta. Okay, and your r goes, let's say, from a to b, whatever these values are, and alpha to beta for the angle, and we're integrating one. Let me make a better looking one. So what are we doing? We're integrating one. One way to think about it is that you integrate in that plane, right? Z is equal to 1. This is Z is equal to 1. So it's this horizontal plane that's parallel to the XY plane. It sits 1 unit above, right? So one way to think about it is you're computing the volume that's under Z is equal to 1 over this region of integration. But volume is also just the area of the region of integration times the height, right? If we're just integrating the volume under a plane. But what is the height? The height is 1. So it's equivalent to just computing the area, okay? This is the area of R, whatever this R is, right? So this piece right here is R, okay? Now, I've said that, right? So you listen to me saying this, and it might not have clicked, okay? And I get that. This might take a little bit of time to really understand. So what you want to visualize is you have your cardioid, right? And then right above it is that Z is equal to 1. Okay, so maybe one way to think about it is this way. So here's my cardioid. Sits, how is that gonna sit? Let me see how it's gonna sit. So something like this, right? Okay, so it sits like this. And then right above it is that plane Z is equal to 1 right here. Okay, and what we're computing this volume under this plane, right? So you can kind of imagine this projection also over here, okay? Um, so if we're computing the volume, but that height is just 1, height is equal to 1, then we're also computing the area, okay? So that's one way to visualize and understand how to use double integrals to compute the area of R. Okay, so we've had enough of that discussion. I think I'm gonna need more paper here to complete this problem. So now let's go ahead and set this up. We'll set it up and then we'll write out the solution on a different page. All right, so what am I going to do? I'm going to integrate 1 r dr d theta. Now I have to be careful. Um, let's see, because of that cusp, I'm going to go from negative pi over 2 to pi over 2. So I'm only going to cover half of this. And over here, I can't do integration and differentiation. Okay, there is a problematic spot, so we can't do that. All right, so that means what? I'm going to double my integral. Okay, and we can do that because we do have a symmetric region of integration, and we just integrate in one. If it was any other function, non-constant function, right? Some function of x or y that you convert into r and theta, we can't do that because one, yeah, okay, one is just that plane, right? That completely flat plane that sits above. We can use symmetry. What about theta? Okay, so theta, let's see, theta actually goes from 0 to 2 minus 2 sine theta, okay, which means we should switch the order of integration, right? Because this is now a function, okay? That's not um, that's not a number, right? So let's go ahead and switch the order. We're gonna go from 0 to 2 minus 2 sine of theta, okay? 1 r dr d theta, and then this will be from negative pi over 2 to pi over 2. Okay, let's go ahead and compute this. Let me copy it. So this is our example 5, I believe. All right, let's go ahead and compute this. Okay, so what do we get here? Let's deal with the inner integral. From 0 to 2 minus 2 sine of theta r dr. Okay, so that would be 1/2 r squared from 0 to this one right here. At 0, what do we get? Everything vanishes, right? So we just need to evaluate this expression squared. Okay? All right, let's see, what do we get? This is going to be 1/2. And what do we get here? 4 minus double the midterm. So double the product, right? The midterm is double the product. So that would be 8 sine theta and then plus 4 sine squared theta. Okay, now if we multiply by 1/2, what do we get? So this is 2 minus 4 sine theta plus 4 sine squared theta. Okay, all right, so that's our inner integral. Okay, what about outer? That would be from negative pi over 2 to pi over 2. And what do we get? 2 minus 4 sine theta plus 4 sine squared theta, d theta. Okay, let's see. Let me double check. So do I have everything? 2 sine squared, 2 sine squared. Did I make a mistake? Oh, yeah, I think you're right. Wait, did I? After distributing the 1/2, it was 4, so it should be 2 over here, right? Right here. And then 2 over here. Okay, let's check. 2 minus 4 sine theta plus 2 sine square theta. Okay, that sounds right. Okay, so now we can integrate all of it, right? We can integrate all of it. So this is 2 theta. This would be 4 cosine theta. What about this guy? So this is 2 times 1 minus cosine 2 theta over 2. So we get 2 and 1/2 cancel out. So we get 1 minus cosine 2 theta. So that would be plus another theta here. And then negative cosine of 2 theta. The antiderivative there would be what? Negative 1/2 sine, not cosine. I'm already integrating sine of 2 theta. Okay. 2 theta plus 4 cosine theta plus theta. Okay, so that's 3 theta, right? Okay, and then if we evaluate this, what are the limits? Our limits are between negative pi over 2 and pi over 2. And I also need to remember that I'll have to double at the end. Okay, all right, so what do we get here? This is 3 theta right here. So that's 3 theta times pi over 2 plus 4 cosine of pi over 2. That's 0 minus 1/2. And what do we get here? Sine of pi, that's also 0. And then minus, okay, 3 times negative pi over 2. And then minus 4 cosine of negative pi over 2. And then plus 1/2 sine of negative pi. What do we get? So a lot of this is 0, right? This is 0, this is 0, this and that. Okay, so we get 3 theta. I don't know why I keep putting this theta in there. This does not need to be here. It's 3 pi over 2 plus 3 pi over 2. Is that right? It's 6 pi over 2. So that's 3 pi. Okay, and then the final answer would be 2 of these. 2 times 3 pi. So that's 6 pi. Okay. All right. So here's your worked out problem where we've computed the area, right? Okay, the area of this cardioid right here by using the double integral. All right. Okay, take a look at this solution. Thanks for catching that typo. I would have caught it eventually when my numbers wouldn't work out, but that's good. I'm glad you guys are watching my steps. So any discussions, anything you want to talk about? Let me know. All right, let's do one more, and then we'll talk about triple integrals. Sketch the region bounded by all leaves of the rows. R is equal to 2 cosine theta. Okay, again, use Desmos for this one. Use a double integral to compute the area bounded by the polar curve. Okay. All right, so we would use Desmos to sketch this curve. We would get something that looks like this. You're going to have one leaf here and one leaf over here and one over here. Okay, except it will look a little bit nicer than that. All right, and it's asking us to compute the area bounded by all of these, right? Okay. Now they are symmetric, or then they're not symmetric. They are the same. So these three leaves, they are the same, which means if we just find one, we triple the result, and that's going to be all of it. Okay. So what we need is take a look at this leaf right here. Okay, so we're going to use this one right here because it's more or less clear what those angles are. Okay, and if it's not clear from the picture, we will be able to compute it algebraically. So I'm going to use this one because I can use symmetry here to compute the area of it. Or if I don't want to use symmetry, I can just use the limits, the upper and lower angle limits to determine what the area is. Okay, so the general setup would be what? The total area, okay, would be 3 times some double integral 1 r dr d theta. Okay, so something is going to go here and something is going to go here, right? So that's the question. Okay, what are we going to put in those limits? Okay, well, for r, it's pretty straightforward. We're going to go from 0 to whatever that function is, right? So in our case, our curve is 2 cosine theta. Okay, so over here, we would say r is going from 0 to 2 cosine 3 theta. What about the angles? Well, you could ask this question, where does this cross the origin, right? So where does our curve, for which angles, that's equivalent to solving a trig equation. 2 cosine theta, or 2 cosine of 3 theta is equal to 0. So that's cosine of 3 theta is equal to 0. There are many solutions, but we know that one of them would be, excuse me, pi over 2 for the argument, right? But the argument is not just theta, it's 3 theta. So theta is then pi over 6. That's this angle right here. You can see by symmetry, this one is negative pi over 6. Let me put it in a different location. Negative pi over 6. Okay, so here's our curve. That's this portion of this curve is going to be generated this way, right? Okay, negative pi over 6. Now notice I don't pick, so what I don't pick? I don't pick 11 pi over 6, right? Okay, not 11 pi over 6 because 11 pi over 6, if we go to increasing, right, the angle needs to be increasing. It doesn't go to pi over 6, right? It keeps going to 2 pi, right? So you find the equivalent representation of that angle so that you have this continuity between limits, negative pi over 6, 2 pi over 6, yes. That's an interval, right? It's a continuous interval. All right, so now we're going to set up our integral for just one leaf. Okay, so that would be 1 r dr d theta. R goes from 0 to 2 cosine 3 theta, and theta goes from negative pi over 6 to pi over 6. Okay, so that is our setup. Why don't you guys take the time and compute this integral? Okay, the answer will be nice. It's going to turn out very nice. So take the time to compute the integral, and then if you once you have an answer, let me know what that is. Okay, the answer for one leaf and then for all of them. All right. Tyler, you have a solution, and so does Carmen look like? Okay. Um, okay. What did you get for your area of just one leaf? Should be a pretty nice answer. Pi over 3. Okay, yeah. Pi over 3 it is. Then the total area is just triple of that, right? 3 times pi over 3. So that's pi. Okay. It's also total volume under z is equal to 1 over this piece, right? Okay. But when area and volume will take the same value, right? Okay. All right, so here is your first portion of the lecture. So that would be double integrals in polar coordinates. Okay, so what's the emphasis on here? Recognizing these regions, these rectangles that are not really rectangles, okay, polar rectangles. We should be able to sketch them. We should be able to read that notation, understand what that actually means, right? And convert it from a graph to the description in terms of algebraic terms and the other way around. Then know that formula. Okay, and the big thing here is no, there's no more x's and y's, and don't forget that factor r. Okay, then the integration steps. Okay, you notice that that sine squared is still here, right? So we still need to remember that formula for the double angle identity. Okay, and then the area connection between the area of integration and double integral. Okay, so now what we're going to do, switch focus and discuss triple integrals. So we're going to do triple integrals today. We're not going to get to too complicated problems. The next time we're going to discuss spherical and cylindrical coordinates. Now for those problems, I usually kind of do like a very light introduction. We're not going to go into too many details. A lot of times I skip it entirely if we're running out of time. I think we're pretty good as far as following the syllabus and the typical outline. So we will go through those topics. But if once you get out of this class, if you feel good about just double integrals in general, double integrals in polar coordinates, and then triple integrals for rectangular coordinates, then I'm good. Then I think that's perfectly fine. Okay, integration in general can be extended to as many variables as you wish, finitely many variables, except it becomes a lot more cumbersome and difficult to visualize. So that's typically why we stop at 3. Okay, so the first thing we'll talk about is triple integrals over boxes. So that's your next extension of multiple integration, right? So we started with um, integral of one function over an interval, right? And then double integral over a function of two variables over a rectangle. And now we have a function that we integrated over a box. Okay. Now, this problem right here, this should have a z at the end. So let's just go ahead and jump in. There's not much theory that we're going to add here. Okay, except now we have 3 variables of integration. So let's go ahead and sketch what we're integrating first, and then we'll compute the actual integral. Okay. Now, of course, we're integrating here 1. So technically, we're integrating a function of 3 variable, right? So that sits in 4 space. And yeah, yes, you cannot visualize it. Or no, you cannot visualize it, right? So that's not something that we have the capacity to visualize, all right? But yes, there are functions of more than just there are functions more than just 3 variables, 4 variables, and multi-dimensional spaces do exist. Okay, we can visualize the region of integration in here. What do we have? We have x that goes from -2 to +2. So let me extend my x-axis here. So let's say this is -2, this is +2. That's where my x goes from. Okay. What about y? Y goes from 3 to 6. So let's say this is my scale. So I'm going to change the scale for y just a little bit so it can kind of all fit in here. 3 to 6, that's my y, right? And then what about z? Z goes from 0 to 2. Okay, 0 to 2. So let's say this is 2, this is 0. Okay, that's my z. Okay, so now I'm going to go ahead and build that box. Okay, so where is it? It is right here. Wait, oh, I did not match this correctly. My x goes from 0 to 2. Okay, sorry. I did not read that correctly. I'm going to go ahead and redo it. Redo all of it. I apologize. Whew, it's Monday. I'm going to blame it on Monday. Let's see. I'm going to read my limits from inside out. X goes from 0 to 2, right? Okay, 0 to 2 for x. All right, from 0 to 2, right here. Let's start over, right? Y goes from 3 to 6, so that one was okay. So let's say this is right here, 3 to 6 for y. And z is the one that goes from -2 to 2. That's it. So here's my 2, here's -2. Okay, now I'm going to go ahead and build my box with these dimensions. So let's see, y is set up, and now I'm going to go 2 in this direction and 2 in this direction. Okay, and then I need to go 2 up and 2 down. And then 2 down. So it should be a box like this. Okay. All right, so that's what my region of integration looks like. My region of integration is a three-dimensional object, right? Okay, in this case, it's a box. So if I were to compute this, how would I do it? Now we're just integrating 3 times. So if I go from the inner dx, that's just x evaluated between 0 and 2, so that's 2. And the next one is with respect to y, so that's 2 dy. 2y is between 3 and 6, so that's 2 times 6 minus 3. Excuse me. 6 minus 3, that's 3 times 2, that's 6. And then the last one, we go from -2 to 2. 6 dz, that would be 6z from -2 to 2, so that's 6 times 4, 24. Okay, what's the geometrical connection here? Well, if we were to just use geometry, how would we find, excuse me, the volume of this object? Well, it would be length, width, and height, right? So for x, we have 2. For y, we have 3. And for z, we have the height is 4, which is 24. Okay, it is no difference. The answer is exactly the same. Okay, so it's good to check this idea. Okay, of what are we computing? The volume, right? The volume of a three-dimensional object. It's a triple integral, and we're integrating 1. Now, what is that 1? Now, 1 now is a function in Bohr space, right? Okay, we can't really visualize it, but it's an extended idea of what we just did for computing the area of integration. Okay, does this make sense, what we just did? I know it might be a little bit tricky because I keep saying there's a function in fourth space, right? And it's hard to visualize it from Euclidean point of view. We can't. Okay, let's go ahead and do an actual computation. So now I have this triple integral where I want to compute the value of it. Now I'm not integrating one anymore. So now I'm integrating a function of three variables. I'm integrating it over a box. I hope you now recognize that, oh, x, y, and z, that what are the limits for them? They're just numbers, so I'm integrating over a box. Okay. So what are the steps? The same as before. I'm going to start with my inner integral. The integral from 0 to natural log of 2. And I'm going to write it as e to the negative x times e to the power y plus z dx. Now, why did I do this? Just to emphasize that e to the power y plus z is a constant relative to x, right? Okay, so this is e to the power y plus z and times now antiderivative. I can compute that, so that would be negative e to the negative x. We evaluate from 0 to natural log of 2. Okay, let's compute this. My constant doesn't go anywhere. And here I get negative e to the negative natural log of 2 plus e to the negative 0. So what do we get here? E to the 0, negative 0, that's 1. And what do I get here? Let's take a look. So this is minus what? This is e to the power natural log of 2 to negative first power. So that's e to the natural log of 1/2. So that's just 1/2, right? So I get 1/2 e to the power y plus z. Okay, so that's done. Now the middle integral. We go from 0 to natural log of 3. What's my integrand? 1/2 e to the power y plus z dy. So I'm integrating now with respect to y, which means 1/2 e to the z is a constant, right? So I'm going to put it in parentheses just to emphasize that that is a constant. The antiderivative of e to the y is just e to the y, so that's nice. We go from 0 to natural log of 3. Okay, so this is e to the natural log of 3 minus e to the 0. And what do we get? That's 3 minus 1. That's 2. So we just get e to the z. Oh, nice. So things turn out much nicer. Okay, then the outer integral, the last one. Notice we're eliminating all these variables one at a time, right? So this is e to the z dz, super simple. E to the z, we go from 0 to natural log of 4. So that would be e to the power natural log of 4 minus e to the 0, 4 minus 1, 3. Okay, right? What does that represent? You might be wondering. 3 what? Units to the 4th, right? We're now in hyperspace. Okay, can't visualize it, don't even try. Okay, it is how much space in R4 is taken under that surface right there over this box. Okay, very abstract interpretation. Okay, but we can keep extending this. We can do this for finitely many integrals, right? So finitely many dimensions. It just becomes a lot more counterintuitive, okay? But yeah, that's what we computed just now. All right, so here's your first triple integral mechanics, right, of how to compute in it. We're computing now integral over function that's just not a constant. This is not a constant function, right? Okay, and over a region that's kind of an extension of a rectangle. This is a box. It's still everything is a constant, right? So all of the limits are constant. Okay. All right, take a look at this. Let me know if this makes sense, if there's anything you'd like to discuss before we get to a little bit more complicated example. How we doing with triple integrals? You guys all got quiet. Good? Yeah? Good for the moment? All right. A lot of students tell me that like they just kind of can't wait. At the beginning of the class, oh, when are we gonna do integration, multiple integration? And once we get there, they're like, oh, okay, well, this wasn't as exciting. But oh yeah, it's just part of the topics, right? Okay. Now, a more interesting examples are those where we're integrating over a region that's not a box. Okay, so let's go ahead and take a look at this example right here. That's going to take some visualization skills. Okay, so work with me here. Try to do your absolute best to see this picture that I'm gonna draw in a minute. Okay, so what do we have here? It says use triple integrals to find the volume of the solid in the first octant, okay, formed when the cylinder z is equal to sine y. Okay, now I know that sounds like our cylinders should look like, kind of like in the shape of a paper towel, right? So that's not what it's going to look like. In this case, the cylinder is just a general term for curves or for surfaces in 3 space. Okay, and we have y is restricted between 0 and pi, and it's sliced by planes. Y is equal to x, and x is equal to 0. Okay, so typically on an online homework, or let's say on a quiz, on a test, I will give you a picture, but I do like to start with an example where we do everything from scratch to just kind of see those big ideas come together. Okay, so all right, let's see. First octant. So it's kind of equivalent to saying, let's stick with the first quadrant where everything is positive, right? What do we have? We have z is equal to sine of y. Okay. Now remember, this is a surface. Okay. This is a surface that's not just a curve. We're now in 3 space. So you might be asking, okay, well, this x is not there, right? So x is not taking any values. When one of the variables is not involved, that means x will take every value, okay, every one of them, okay. But you could just plug this into Wolfram Alpha to see what that looks like, okay, for just z is equal to sine y, okay. Well, one way to visualize it is this. Let me see if I can just kind of make a projection. So now let's say this is just z, y plane. Okay, what does that look like? Sine of y, if I'm just sticking to a two-dimensional space, you say, okay, yeah, of course, that looks like this curve right here. So it's going to go through 0, 0, and then it's going to go like this, right? Okay, so that's a curve that we're very familiar with. Let me actually give it a little bit more um, goes infinite this direction and infinite in this direction. Okay, so that's a curve that you're very familiar with. Now, we also have x. So what does that mean? Now you can imagine kind of x is going in this direction. Okay, this is our x. And x is going to take every value. So it's a sheet, right? You imagine this infinite sheet that takes this wave form along the y-axis, okay? But it's infinite for the x direction and in both directions, okay? So one way to visualize it is like this. So here's the sheet that kind of looks like this, okay? And then it goes that way, except in the x direction, it's this infinite sheet. Does that make sense what I'm trying to show you guys? You might have to just trust me on that one, that that's what it's going to look like. Okay, so um, try your best to visualize what we're working here with. Okay, and if it doesn't work, just put it in Wolfram Alpha to see what the picture is going to look like. Okay, now let me go ahead and make it a nicer picture, what it's going to look like once we restrict it. Okay, so what I'm going to be looking at is something like this. Let's see, it's going to look like this right here. That's part of that curve, of that surface. So this surface right here, z is equal to y, oh, sine of y, not y. So that's going to be my surface. That's portion, this portion right here. Okay, and y is equal to z, and y is equal to x, sorry, that's this one right here. That's also a plane. Okay, which plane is it? It's a plane that's the straight plane that goes through that curve right there. This is y is equal to x, except what I drew is just a curve. What you should visualize is this plane that goes straight up like this. Okay, so now what we have is this solid. Okay, that is not a box. There's curvature here, right? Here's my solid, the solid object that I would like to compute the volume of. So what are our walls? You can think about, the different walls that we have. So we have that triangle that's kind of like the base in the XY plane. Okay, then we have this piece right here, and then we have that other piece right here in the ZY plane, and we also have that top, right? So let me color this top right here. Okay, so that's what we want to find the volume of. All right, so how do I do this? Let's go ahead and set up. It's a triple integral. I'm going to compute 1. That's going to be my integrand. I'm going to integrate 1. All right, and now the question is, what are my limits? So if let me remind you that for double integral, what did we do? Let me do a quick reminder here. For double integral, we had, let's say, f of x, y, and if we went in the y direction first, then we would say, what is our y? Some curve in terms of x, and then the other one is also in terms of x, but maybe a different curve. And then here for x, we had limits, let's say from a to b. Okay. A very similar situation here, except now the way I think about it is I go from surface to surface for the integral, and then from curve to curve, and then from point to point. Okay, so now my inner limits are these walls, they're surfaces. Okay, so I'm going to integrate 1. I'm going to go in the z direction. Okay, I'm looking at this piece and say, do I have top and bottom, the clear top and clear bottom, and their surfaces? Okay, yes. So my z is just equal to 0 as my bottom curve. That represents this triangle right here. Okay, that's like the bottom, the base of my object. What about the top? Well, the top is z is equal to sine of y. Okay, so that's my first direction. Then, well, then you can decide which direction should we go second. Okay, so I chose to go in the x direction. We're going to set up both of these integrals in the x and the y. If I go in the x direction second, okay, so let me indicate what that direction is. This is the direction. So now I go from curve to curve. X is equal to something. Okay, what is it? So it's this curve right here, and that's just x is equal to 0. To which curve? This curve right here, that's x is equal to y. Okay, from wall to wall, done. From curve to curve, done. Now we go from point to point. Okay, now if I go in the y direction, my smallest value for y is 0. Okay, so y is equal to 0. Oh, it says right here, right? And then this edge right here, that's y is equal to pi. So my upper limit here would be y is equal to pi. Okay, that's one way to set this up. Or let's go ahead and set it up slightly different. We're still going to do dz first. Oh, let me put dy here. But now I'm going to rewrite as dy and then dx. For z, nothing changes. We go from 0 to sine of y. What about y? Now I'm integrating in the y direction second. So what are my curves going to look like here? Okay, if I'm integrating the y direction, I'm going from this curve right here, and I'm going to highlight it in red, to this one. So this is y is equal to x, and we'll go to up to y is equal to pi. Okay, and then what about x? Now x goes from point to point. We go from 0 to whatever this point is, right? Okay, so now the question is, what is that point right here? Well, this is where y is equal to x and y is equal to pi intersect. So this is, of course, x is equal to pi. Okay, so these two integrals are two equivalent but slightly different ways to set this up. And now you can see if you integrate the first one, you get a function of y, and then you integrate it with respect to x, you're gonna get rid of x and you're only gonna get a function of y as your last integral, right? Similarly, for the other one, you're gonna get as a function of x at the end. Either way, whichever way you do it, you're gonna get pi. Okay. All right, so here's this first example of triple integral where we do not have a box. We do not have something as simple as just a box, right? So I think these are probably the most challenging integrals for multiple integration portion. I don't even think cylindrical integrals are that difficult, but these can be really tricky, all right? So I'm going to stop right here. We will cover example 4 next time. We'll use it kind of like a warm up. But what do you guys think? This example right here. Any feedback? Anything you want to discuss? All good? How are your visualization skills this morning? it might take some time for you to kind of wrap your head around what that, how that works. Okay. And that's okay. Don't get frustrated if something is not obvious. Okay. It's not like it's obvious to me because I've done this for many, many years, right? But it's not the expectation that you all automatically say, oh, sure, sure, I got this, right? No, like really think about these pictures, play with the graphing utilities, think about it, let these problems sit in your mind for a little bit. But yeah, typically students don't like this particular problem. I used to put this one on an exam and then I stopped. I said, oh, let me just work through it in an example instead. Okay. All right. Then we will stop right here. I'm gonna go ahead and stop the recording.